Okay, let's get started. So in this short video, I want to discuss how we can solve maximum bipartite matching by reduction to max flow. And this is an important idea because reductions are useful not only for tractable algorithms, but also for proving hardness results. So this would be good practice for uh, later part of the course where we talk about NP complete reductions. But let's first look at a polynomial time reduction of one algorithm to another algorithm. So in this case, in the class, we talked about the max flow algorithm. We talked about Ford-Fulkerson algorithm and Dinitz's algorithm, Edmond-Karp's. So uh, we want to see that how we can apply Maxflow to solve other problems. And that means if we have an instance of, let's say, a bipartite matching problem, and we want to solve this problem, then if we know an algorithm for Maxflow, then we can use that as a black box to solve bipartite matching. So let's see how that works. So let's say we have this black box which solves Maxflow. Right? So that means it needs an instance of a graph uh, and two special vertices S and T and capacities on every edge. And then, so we have a graph and two special vertices S and T, and that goes into this black box, and we return a flow. Right? And then now we want to use this to solve the bipartite matching problem. So what is the bipartite matching problem? So the problem is we are given a bipartite graph, which means we have two set of vertices like this. And let's call this set A and this set B. And we have edges going from here to here. Okay. And what we want to do is we want to find out if we can choose the maximum number of edges that where each edge has one endpoint in A and one endpoint in B, which is all the edges, but no two edges share a common endpoint. So for example, if we were to choose this edge, then we cannot choose this edge anymore, right? Similarly, this edge is also not possible, but we are okay to choose this edge, and then we can choose this edge, and then this edge is also possible. So that's the maximum number of edges that we can choose, and the problem is to find such a maximum matching. Okay, so now how do we solve this problem? So our approach is we're going to change this instance of a bipartite matching to an instance of max flow, and then we want to solve bipartite matching using a solution to max flow. So let's see how that works. So let's take an instance of bipartite matching. And let's use the same graph. So it's going to have these specific edges. So, so how do we convert this to an instance of max flow? So we're going to introduce two new edges. So let's call two new vertices. So this will be called S, and we're going to call this T. And then we're going to add additional edges from S to every vertex in A, which is the first set in the bipartite graph. And then the second set is B. We're going to add edges from B to this terminal vertex. And then we're going to give these directions. So everything flows from left to right. Okay. So that's our graph that we formed. And this looks like a graph which can be solved with max flow. Right. So now the next thing we need to define some capacities. So what we're gonna do is that we're gonna give everyone capacity 1. So all the edges are gonna have a max capacity of 1, and we'll explain why that is the case. So why is the edge capacity 1 everywhere? Because we want to use this flow to select a maximum bipartite matching. So now let's say we want to find a flow. If we choose a flow of 1 here, if we send flow of 1 here, then only 1 can go out from A to B. That means we're going to choose just one uh, edge that touches both a vertex in A and B. So we're going to just choose this one. Let me change the color to make it clear. So we're choosing this edge, and this passes through here. And now this flow conservation, so one goes in, one goes out, means that I cannot choose this edge anymore because that will violate the constraint. And that means that we cannot have two edges that have the same endpoint in A. Right? And now if I send a flow of 1 across this one, now I have two edges outgoing from this vertex, and I can choose just one of them. So I can choose, let's say, this one. Okay, and that again is satisfying the constraint of bipartite matching. If I choose this edge and send a flow of 1 here, again, there are 1, 2, 3, 4 vertices. So I can just send flow of 1 across this. So let's say I choose, and then again, if you see, I cannot choose this edge because 1 is already flowing through here. And if I send 1 here, I can only send out 1 across here, which means I cannot choose this because that would violate the flow constraint. So my only option is either choose this edge, and there is no other option because this edge I cannot choose because I've already blocked the flow here. So let's say I can now choose this one. Okay. And then finally, if I send a flow along 1 here, and then I have two options. Now I cannot choose this one because this is blocked because flow 1 is already going to this vertex. So I can just send 1 across here. And then this one can now flow back here to the terminal. This can flow here, and this can flow here, and this can flow here. So this means that if we solve max flow on this extended graph, we actually get a maximum bipartite matching in the original graph. So that's a reduction. We reduced an instance of bipartite matching to the max flow problem. And by solving max flow, we get a solution to the bipartite matching problem. So that is how we can reduce bipartite matching to max flow and solve bipartite matching using a max flow algorithm. And then any of the max flow algorithms like Ford-Fulkerson, Edmond-Karps, or DNX can be used to solve this bipartite matching problem. All right, that was a short discussion on how to reduce bipartite matching to max flow. Hope this is useful. Thanks.